welcome to the deep dive. This time, we're going to be taking a close look at a research paper that's really trying to tackle a pretty big challenge in machine learning. How do we build systems that are not only, really high performing, but we can also show that they're safe and secure.
Right.
So this paper is called Bridging Formal Methods in Machine Learning with Model Checking and Global Optimization.
Yep.
And it just came out last month, December 2023.
It did.
So it's really cutting edge. And, given your expertise in both formal methods and machine learning, I'm really excited to hear your thoughts on this. So the paper starts off by talking about, the limits of that traditional V model that's used in software development.
Right. The classic V model visualized in Figure 1 of the paper works well for traditional software.
Yep.
But it kind of falls apart when you get into machine learning development because of the iterative and data-driven nature of that development.
Yeah.
So they propose a new V model specifically tailored for machine learning.
Interesting. So can you walk us through the stages of this new model?
Certainly. They outline a number of key stages: operational profile and data collection, requirement and specification, architecture and hyperparameter, model training, testing, and empirical evaluation, verification and validation, and finally, operational reliability assessment.
Got it. So each stage has its own unique and opportunities for using formal methods.
Yeah, it's like integrating a safety net into each step of the process, so you're not just hoping for the best at the end.
Yeah.
Now, to formally specify the safety and security properties, they've introduced a new language called MLS2, which is short for Machine Learning Safety and Security. Yeah.
So before we dive into the specifics of MLS2, can you just give me a sense of why
we even need a new language for this?
Well, most existing formal languages are designed for deterministic systems, whereas machine learning is all about probabilities, uncertainties, and these complex data distributions.
Right.
So MLS2 gives you a way to formally talk about and reason about those aspects.
So you're creating this precise mathematical language that can handle the uncertainty that's inherent in these models.
Exactly. And in fact, they use this language, MLS2, to define 10 different safety and security properties that are critical for building reliable systems that use machine learning.
That's great. So let's break those down one by one.
Sounds good.
Maybe starting with generalization.
Sure. So generalization is all about how well a model will perform on data that it hasn't seen before.
Right.
Not just the data it was trained on.
Makes sense.
And in MLS2, they capture that by analyzing the expected loss over the entire data distribution.
Okay. And what about uncertainty? How is that formalized in MLS2?
So uncertainty is the model's ability to tell you how confident it is in its predictions, right?
Right.
So MLS2, you can use it to set limits on the model's posterior distribution and make sure that it actually reflects how uncertain it is about its predictions.
So instead of just saying, this is a cat,
exactly,
should be able to say, I'm 95% sure this is a cat or something.
Exactly. Right. And that kind of transparency is really important, particularly when you're talking about safety critical applications, like, let's say, medical diagnoses.
Absolutely.
Yeah.
Okay. What about robustness?
All right. So robustness focuses on how well the model can resist what we call adversarial attacks. These are deliberate attempts to manipulate the input to make the model make mistakes.
So if somebody alters an image just slightly to fool a self-driving car.
Yeah.
Right.
That's a great example.
And so a robust model would still be able to identify
those objects.
Correct. And with MLS2, you can actually specify how much perturbation the model can handle before its output changes significantly. So it gives you a way to measure robustness.
Fascinating. What about attacks on the training data itself?
Right. So they also address that. So data poisoning, where someone injects malicious data into the training set is a very serious threat.
Totally.
But MLS2 lets you put constraints on the training data distribution to help detect and stop these kinds of attacks.
So you're building safeguards into the training process itself.
Precisely.
That's clever. And they talk about backdoor attacks too, right?
Yes, so backdoor attacks are when you have this hidden trigger in the input.
Okay.
And that can cause the model to produce some specific output.
Got it.
That could be harmful.
So how does MLS2 help counter that?
Well, you can use MLS2 to analyze how the model behaves when it's given different input distributions, including ones that have these potential backdoor triggers.
So it can help you detect and neutralize those vulnerabilities.
Exactly.
Like, that's amazing how it can give you that level of detail.
It's very powerful.
So what other properties do they cover?
See, the next one is model stealing.
Okay.
Which is where an attacker tries to create a copy of your model.
Oh, wow.
Just by making queries to it.
So they're essentially trying to steal the model's knowledge without having to train it themselves.
Yeah.
So how does MLS2 help prevent that?
Well, with MLS2, you can set limits on how much information can be taken from the model's output.
Right.
So it makes it harder to just copy the model's behavior.
Got it.
Yeah.
Makes sense. What's the next one?
Okay, so next we have membership inference attacks.
Okay.
These attacks try to figure out if a specific data point
interesting.
was used to train the model.
Wow.
And MLS2 can help you quantify the risk of those attacks.
Okay. By looking at how sensitive the model is to individual training examples.
So if the model's output changes a lot.
Exactly.
When you add or remove a particular data point, that could indicate a vulnerability to these membership inference attacks.
That's right.
Right.
And that has big implications for privacy.
Totally.
Especially when you're dealing with sensitive information.
Big time. Are there other privacy-related properties that they consider?
Yeah, they also talk about model inversion attacks.
Okay.
These are attempts to pull out sensitive information about the training data by looking at how the model behaves.
Got it.
So MLS2 gives you a way to specify exactly how much information can leak out through the model's output.
So it's about assessing and mitigating those privacy risks.
That's right.
Okay, so it's not just safety and security, it's privacy too.
Exactly, which is becoming super important these days.
Huge. What are the last two properties?
Okay, so the ninth one is interpretability. Okay.
Which is about understanding why the model makes the decisions it does.
Got it.
You know? And with MLS2, you can set constraints on how the model is structured. Or how it makes decisions.
So it's not enough for a model to just be accurate.
Exactly.
We need to understand why it's making the decisions it's making.
Precisely.
Especially in fields like healthcare or finance.
Absolutely.
Where transparency is really important.
It is.
Okay, and what's the final property?
Okay, the last one is fairness.
Okay.
Which is about making sure that the model isn't biased against certain groups or individuals.
Got it.
So MLS2 lets you actually write down these fairness criteria.
Wow.
And then analyze if the model's predictions are actually fair.
Okay, so they've laid out these 10 properties in MLS2.
That's right.
But how do they actually verify them?
That's where things get really interesting. They suggest using global optimization methods as a core part of the verification process.
I'm eager to dive into that.
Yeah, but maybe let's pick up there in the next part of our deep dive.
Sounds good.
Welcome back to the deep dive. We left off talking about how the authors of this paper propose using global optimization techniques to verify the safety and security properties they've defined in their new language, MLS2. Can you elaborate on how global optimization fits into this verification process?
Yeah, so global optimization methods are basically algorithms for finding the best solution to a problem, even when the search space is really complex and high dimensional.
Okay.
So in the context of machine learning verification, what that means is we're trying to find the inputs or scenarios that are most likely to make the system violate those safety and security properties.
So it's like a stress test.
Exactly.
Deliberately trying to find the weak points.
That's right.
By looking for those worst case scenarios.
Yeah, and the authors are arguing that this is really powerful for finding potential vulnerabilities that you might not see with normal testing.
Got it. So they discuss a few specific techniques within this framework.
Yeah.
Can you walk us through some of those?
Sure. One of the key ones they highlight is Markov Chain Monte Carlo, or MCMC.
Right.
It's a way to sample from complex probability distributions, like the posterior distribution of a model's parameters.
So for our listeners who might need a quick refresher, can you explain what the posterior distribution represents in this context?
Yeah, so the posterior distribution basically captures our beliefs about the model's parameters. After we've seen the training data,
right,
it takes into account our prior assumptions
Got it.
and the evidence from the data.
So by sampling from this distribution using MCMC,
Right.
we get a sense of which parameter values are most likely.
That's right.
Given the data we've seen.
Precisely. And that lets us analyze how the model might behave in different situations, including ones that might lead to those safety or security violations.
Okay. And then they also discuss variational inference or VI. How does that differ from MCMC?
So ZNIF is trying to approximate the posterior distribution with a simpler distribution that's easier to work with computationally. It's like finding a simpler representation of that underlying probability landscape.
So it's a trade-off between accuracy and computational efficiency.
You got it.
What about the data itself?
Right.
How do they use global optimization to analyze the properties of the data distribution?
So for that, they use kernel density estimation, or KDE.
Okay.
And this technique basically estimates the probability density function of a data set.
Got it.
So it gives you this smooth, continuous representation of how the data is spread out.
And having that estimate is really important for analyzing things like generalization error. Right.
Absolutely. Generalization error is all about how well the model will do on new data that it hasn't seen before.
And if the training data isn't representative of the real-world data, the model's performance could really suffer.
That's right.
So KDE helps us understand those characteristics of the data and identify potential problems that could affect generalization.
You got it.
Okay, so they're using these techniques, MCMC, VI, KDE, to verify these safety and security properties in MLS2. But they also acknowledge that these methods aren't perfect. They talk about these error bounds.
That's right.
Can you explain why those are so important in this context?
Sure. So unlike formal proofs, which give you absolute certainty, statistical verification methods always involve some estimation and probability.
Because there's always a chance for error.
There is, and error bounds give us a way to measure that uncertainty. It's like saying, we're not 100% sure, but we're confident the true value is somewhere within this range.
Got it. And understanding these bounds is crucial for interpreting the results correctly.
Absolutely.
And figuring out how much confidence we can have in the system. And they point out this challenge related to these error bounds. How they propagate through those operations in MLS2. What do they mean by that?
That's a good question. So when you combine multiple properties using things like ND or NER, the uncertainty in each property can affect the overall uncertainty of that combined statement.
So it's like a chain reaction.
That's a good way to put it.
Where the uncertainty in one part of the system can cascade and amplify throughout the entire process.
And that's an area where more research is definitely needed to develop more reliable techniques.
Got it. Now, in addition to these techniques, the paper mentions using diffusion models for verification. Diffusion models have become really popular lately for generating images and text and even music. So how do they see these generative models being applied to verification?
Well, it's still early days, but the idea is to leverage their ability to learn and represent complex probability distributions.
So instead of using MCMC or VI, we could use a diffusion model.
Potentially.
To capture the nuances of those distributions.
That's the idea. And they suggest a couple of potential applications. First, they could be used to generate a bunch of different inputs or scenarios to test the system, especially in those hard-to-reach corners of the input space.
So it's like an AI-powered test case generator.
That's a good way to think about it.
That can help us find vulnerabilities that we might not have even thought of.
That's right.
And second, they could be used to estimate the posterior distribution of the model's parameters, potentially as a more efficient alternative to other methods.
That's right.
So diffusion models could play this dual role in verification.
They could.
Both generating test cases and helping us understand the uncertainty in the model itself.
Precisely. And I think that really highlights how interconnected different areas of machine learning are becoming.
Totally.
And the potential for sharing ideas across those areas.
Well, we've covered a lot of ground in this part of our deep dives.
We have.
We've talked about global optimization techniques like MCMC, VII, KDE for verifying these properties in MLS2. We've also talked about the role of error bounds in understanding the limits of these methods. And we've even touched on the potential of diffusion models.
It's exciting stuff.
For this field.
It is.
It's clear that ensuring the safety, security, and reliability of these learning-enabled systems isn't just some theoretical thing.
It's not.
It's really important as these systems become more and more
Absolutely.
integrated into our lives.
That's right.
In the final part of this episode, we'll talk about some of the open challenges and future research directions in this area.
Sounds good.
Welcome back to the deep dive. We've, really explored the landscape of these safety and security properties in machine learning systems.
Yeah.
We've talked about the methods for verifying them, using, global optimization techniques, and even touched on, the potential of these diffusion models.
Yeah.
Now I kind of want to turn our attention to the future.
Sure.
What are some of those open challenges?
Yeah.
And those exciting research directions that are kind of out there?
Well, the paper definitely lays out a vision
Yeah.
for a future where these systems
Yeah.
are not only powerful,
Right.
but also demonstrably safe and secure and reliable. But as with anything ambitious, there are definitely some hurdles to overcome.
Totally. And one of those key challenges that we've kind of talked about throughout this whole deep dive has been computational complexity, right? As these models get more and more complex and the data sets get larger, the computational demands of these techniques can really become a bottleneck.
Absolutely. And finding ways to make those methods more tractable is super important.
Yeah.
For wider adoption.
Now, the authors suggest exploring these approximate verification techniques.
Yeah.
Can you talk a little bit about what that means?
Sure. So the idea is to find a balance between accuracy and efficiency.
Okay.
Right? Instead of trying to find the absolute best solution, which might be computationally impossible, we aim for a solution that's good enough, that gives us reasonable confidence without needing tons of resources.
So it's about finding that pragmatic compromise that lets us apply these techniques to real-world problems on a reasonable timescale.
Yep.
Are there any other promising directions for addressing this challenge?
Yeah, I think the development of specialized hardware and software tools is really exciting. Instead of relying on these general purpose tools that might not be optimized, we can create tools specifically for this that exploit those unique characteristics of machine learning models.
It's like having the right tool for the job.
Exactly.
Now, beyond computational complexity, there's also the challenge of these error bounds.
Right.
As we talked about before. These methods inherently involve some probability and estimation, which introduces uncertainty. And we need to be able to quantify that and control it.
Absolutely. And understanding how those error bounds kind of move through the whole verification process is really important.
Right. So if the errors are allowed to accumulate,
they
could really affect the reliability of the whole thing.
That's right.
And the authors actually say that this is an open research question.
It is.
So we need to do more work to figure out how these error bounds interact.
That's right.
And how they affect that overall confidence in the system.
And that's going to require a deeper understanding of the statistics involved and how they connect to the formal language being used.
So it's really a reminder that this all requires expertise.
It does.
From many different areas.
Yeah.
You've got statistics, formal methods, machine learning.
Right. The authors really emphasize the need for collaboration between these different fields so we can come up with these more robust and sophisticated techniques.
Yeah, so formal methods people bring their rigorous analysis and proof techniques.
Right.
And the machine learning folks bring their knowledge of these complex algorithms.
That's right.
And it's this really cool symbiotic relationship where everyone can kind of learn from each other.
Absolutely. And as these fields continue to converge, I think we're going to see some really amazing research come out of this.
This deep dive has been a fascinating look.
It has.
At this rapidly evolving area of research.
Yeah.
We've talked about this new formal language, MLS2.
Yep.
We've explored some powerful techniques for verifying these properties. And we even got a glimpse of how diffusion models could be used in this space. And, it's clear that ensuring the safety, security, and reliability of these systems is not just an academic thing.
It's not.
It's really important as these systems become part of our everyday lives.
That's right.
And this paper gives us a really compelling roadmap.
It does.
For building that trust. Through rigorous analysis, formal verification, and a deep understanding of this connection between statistics, logic, and machine learning.
And as research continues, I think we can look forward to a future where AI systems are not just powerful, but also demonstrably safe and secure.
And trustworthy.
Absolutely. That's a future worth working toward.
Totally agree. Thanks for joining us on this deep dive.
Thanks for having me.
Until next time, keep exploring, keep learning, and keep asking those tough questions that drive innovation in the world of AI.